Well, good morning, good afternoon, good evening, wherever you are on the fourth world. I'm Bill Ragsdale. I'm the founding president of the Fourth Interest Group. And today we are going to have a presentation on Bill's Does. Actually, I use the original phrase, Bill's Does. Of course, it's now known as Create Does. We'll go into some of the history as the presentation proceeds. So the history of Create Does started in 1969 or a little bit before that when Charles Moore invented it. He started out with the Bill's Does as the construction. In 1982, he redefined or gave us a new formulation known as Create Does. And then finally, we'll talk about the current 2023 methods that are used in Win32.4. So what does it do? Well, Create Does creates words. It creates words. Might call it a meta-defining word or an ultra-defining word. It operates one level above words like colon, comma, colon, variable, constant, and so on. It can be used to create those words, or you can actually use it in metaphor to define a complete fork. Also useful for defining database fields, as we'll see in a few moments, and of course, assemble opcodes. Most fourth metacompilers have an assembler, and it is written using Create Does. So generally, the factor on these words are that they have a common structure. For example, variables have their individual names, but they will have a particular memory location associated with them. So how's this done? Well, the parent word, and for today's work, we'll use the word parent, although it can be any word you choose. The parent word will create a family of child words that share a common execution, but have individual parameters. And our discussion today will take those two elements apart, the common execution and the individual parameters. Here's an example. It's a silly word that really doesn't do anything, but we're defining the word parent, which uses create and comma. This will create a child word, and it will save a parameter for that word. The does part will be executed for that child word. So when child executes, it will do a fetch and a drop. See some examples. We'll define the word constant using Create Does. So Create creates the word name, and comma puts the parameter of the constant into memory. Does simply fetches that value back. And we see down the next line down is the hex 10x, which we define as hex base. So every time hex base executes, the address of the parameter goes on the stack and the fetch fetches it. This is an example of defining opcodes. Opcodes are a little bit more involved. They create comma, names the opcode, and takes its hex value saved as a parameter. Then when that opcode is executed, the parameter is fetched back and the comma compiles it into memory. We see some examples there. 5F, hex value of 5F, X5F is the equivalent of a clear carry. Hex BB is the opcode for push. So executing push will place BB in memory. As an example, in a field for a database, this assumes a linear database, as an array. Create will create the name of the field, and then over, comma, plus determines the current offset into that database, and the plus calculates the offset to the next term. When this executes, the fetch sign will pull the value, the current offset value of that field, and then add it to the origin to give us the dedicated memory spot within that array. So we see here, we're building, the fields are name, age, and weight. The field name is 20 characters long, and its origin as at 0. After that executes, if we use field will take the offset of 20, assign it to age, and it will add the size of a cell, which is 4 bytes, to age to generate the next word, which would be weight. And so weight would be at 24 bytes into this array. And at the end, we drop the accumulated parameter. Executing each of these names will put its offset physical address onto the stack. So rewind to some history. In the 1960s, from about 1966 to 69, when Charles Moore was developing forth, he created the bills does form. We see the use here. The parent word uses bills, comma, does at dump, very similar to what we saw with create. The blue at the bottom is the words that are compiled into memory. The parent header is the full-length header that defines the word. Do is a code to execute a colon definition, and then it simply combines bills, comma, does at drop and encode. The child header has does in it, and we'll see how that is added in, and then it has a pointer to the execution code. So the parent takes care of building the word, and then the child header has the does and the pointer to the execution code. Here's how it's actually developed. The bills word executes 0 constant. It builds the header and it reserves 1 parameter in the parameter field, temporarily at 0. The does all the work. This rewrites the parameter field of the calling word. That's the 0 that was just defined. And it rewrites the code field address to point to the does code. The rewriting of that is done simply by the rfetch latest PFA store. That ends up rewriting the code field of the most recent word. And semicolon code takes care of all the minutia. It controls the fourth nesting. It loads the address into W of the high-level code, and then it jumps to execute that code. In 1982, Chuck introduced the new does. So you see now we have the very same code, except bills has been replaced by create. In the compiled form, the code field contains do colon, and then create comma, and then does has compiled inline this paren, do does greater than, closing paren, and a 4-byte cell pointing to the following cell, which contains a subroutine called jump subroutine do does. This little code is the magic inside that makes the child word link to the code that follows the @ sign and the drop. So the child header, its code field address points back to that cell that contains the address 1 byte, one cell ahead. So for those of you in the know, this is the very same structure that a code word enjoys. You have the code field address pointing to a forward pointer and then pure machine code. So Chuck's method in this is to use the subroutine call to locate the source of the code, the @ sign and the drop. So the paren does creates this fake code word that is the here plus cell and the jump subroutine. And when child executes, it locates the inline code that holds the 1, 2, 3, 4 placed on the stack, and then it jumps to execute that @ sign and drop. The advantages. Well, first, we no longer need the word bill, so it saves 1 word that has only 1 purpose. And now we share the use of create. It uses the inline code for our interpretation. That's the little magic in the middle, but it has a cost. And that cost is there's an extra pointer in the child word that is not needed in the old format. In the old format, the child word has this extra parameter, and with the new structure, that extra parameter is no longer needed. And finally, tick will properly return the parameter address in child. As we'll see in a moment, having that extra value in the child word and in the bills does form means that tick returns the address one cell before where it actually should return. So how do we do this in Win32.4? The key element here is that all code must be in the code memory allocation. This is due to the split headers. Code words have their header in the application dictionary, application portion of the dictionary, but the actual code must be in the code segment. So therefore, this simulated inline code can't be used. So Andrew came up with a solution. And what he does is he places the little code fragment into the code portion and then uses the create does defining words to locate that. They locate that runtime portion of the child word. And then the normal do does is executed. So the paren do does greater than paren is the key. It creates this unnamed code fragment, which I'm calling proto do does. This is tucked away in the code portion of the memory. It's a silent process. It has no head. It is just a short snippet of code. The proto do does places uses the move to W the execution address in parent. This means that in register W, we now have the address of the high-level code in the parent word. This is done by compile. Then we compile a long relative jump to the existing do colon. And do colon does as we expect. It places the child's parameter address on the stack, directs execution to the address in W, and then execute next, which takes us to that high level, interpreting that high level code in the parent. Here's a picture of how it's done. The parent word creates a new word. It executes do does. We have the proto code in line, fetch the drop and unnest. In the child word, the code field address in the child word points to the proto does. In the proto does, we see the machine code for moving W, taking the address from after the proto does. Now, the address after the proto does is the machine code or the high-level compile code that it's going to jump to. Then it jumps down to do does, and we go through the regular steps of preparing for the interpretation and putting the parameter field address on the stack. So we've seen three different methods. We've seen the original bills does. We've seen the original create does. We've seen the bills does that came in set in 82, and we see the current value. Now, Chuck introduced this at the formal conference in 1982. When he simply described it in about 4 sentences, the place went silent for about 3 seconds, and then broke into a hubbub of discussion as people in their head did the compiling process, visualized what the code structure looked like, and saw what a beauty it was. There's another approach to this process, which uses semicolon code. We'll discuss that some other time. So as conclusion, the create, does, and semicolon code can actually be used as the core of a meta compiler. In doing this, there would be a number of forward references, but every word that in a fourth system can be defined by create, does, and semicolon code. Currently, in the meta compiler, these words are just adjuncts and used to define a few other words, such as in the assembly. So we've seen a quick tip through the history of create does from about 1969 to the current. I hope you all found it useful. And now I'll return back to Kevin, our fearless leader.